Today we're going to talk about section 2.1 on the basics of functions and their graphs. I am going to split this lecture into two parts. Part 1, just going over the basics, vocabulary, notation, etc. So we're going to start off with a couple of definitions. So the definition of a relation is simply any set of ordered pairs of the form XY. The domain, which we will be talking a lot about domain and range this semester, the definition of the domain is the set of all first components of the ordered pairs, which is usually the variable x. The range is the set of all second components of the ordered pairs, which is usually the variable y. In order for a relation to represent what we call a function, that means that we have a relation in which each first component, or the x value, gets assigned to exactly one second component, or y value. In other words, each x can only be paired with one y. So we should be able to use that definition to decide if a relation is a function, if it's given in ordered pair form, equation form, graph form, etc. So our first example is using a relation defined as a set of ordered pairs to decide whether or not it's a function and then to state the domain and the range. So for the first example, we have the set of ordered pairs 3, -2, 5, -2, 7, 1, and 4, 9. So the first question is this a function? And our answer here would be yes, because no x's are repeated. The x value 3 goes to one y value, the x value 5 goes to one y, the x value of 7 to one y, and the x value of 4 to one y. So since no x's are repeated, this is a function. The domain represents the set of all first components. Since this is a finite set of numbers, we simply list the domain as a set of numbers. So inside of these set braces, we're going to list all the first components, or x values, 3, 5, 7, and 4. In MyMathLab, if they tell you that that's wrong because it's not in order, it just means to reorder them from smallest to largest, 3, 4, 5, 7. The range, again, we're just going to list the numbers because we can see all of them in our set. So we're looking for the second components, or the y values. So we have a -2. We do not need to list it twice, even though it occurs twice. 1 and 9. So the different y values from our set are -2, 1, and 9. So we're going to do another example of the same directions. This time our set of ordered pairs contains the ordered pair -1, 3, 2, 4, and -1, 6. So the first question, is this a function? In this case, we would say no, since the x value of -1 is paired with a 3, but then again, it's also paired with a 6. Remember, the definition of a function says each x can only be assigned to one value of y. And since that is not the case here, this is not a function. In other words, an x value repeats. We can still list the domain and range. So the domain, set of all x's, we have -1 and 2. So those would be our only two x values within our set, and then our y values are 3, 4, and 6. So that would be our range. Since these two examples show a finite set of ordered pairs, we can list the domain and the range as sets of numbers. Later we will look at domain from a graph, and then eventually in the next section we'll see it from an equation, in which we will be using interval notation. Our next example says determine if the equation defines y as a function of x. So not from a set of ordered pairs, but from given an equation. So again, we're looking for, does y equal one x value? So each x gets paired with 1y. So if we're wanting to know if it defines y as a function of x, if we solve for y and it equals one result, then that's going to mean it's a function. So in this first example, x squared plus y equals 25. So if I was solving this for y, we would subtract x squared from both sides to get y by itself, so I could rearrange it to look like this. Y equals 25 minus x squared. So y represents this one value for whatever x I choose. In other words, I choose an x, I square it, I subtract that number from 25, and every time I do that, I get one result. So yes, this is a function. In part B, we have the equation 4x equals y squared. Same question, is y a function of x? This time, if I were to solve for y or get y by itself, I would have to square root both sides. So when I square root this side, I would just get y, but remember when we square root both sides, we have a plus or a minus that has to go in front. So getting y by itself by square rooting gives me y equals plus or minus the square root of the 4x. So notice here when I solve for y, I get two values. I get both the positive and the negative of whatever the square root of 4x is. So in other words, I get two values. Given one x plugged into here, I get two results for y. So that means this is not going to be a function. For example, let's just try x equals 1. If you plugged in a 1 for x, you get the answer plus or minus the square root of 4. In other words, both positive and negative 2 would be y values for that one single value of x. So that violates our definition. From an equation, one way you can usually tell if the power of y is even, like it was here, it is not going to be a function because that's going to require the plus or minus sign when you get the y alone. If the power of y is odd, like it was here, even if it was a third power or a fifth power, taking an odd root does not require a plus or a minus. So that's going to be a function. All right, so now we're going to move on to using what we call function notation. All right, so if y is a function of x, we can represent y using what we call function notation. And that is the symbol, typically f parenthesis x close parenthesis, and we would read that as f of x. In other words, given an x value to plug into our function, the function f represents the value of the function for that number, so it represents the y value for the x that you plug in. So f of x is the y value of, or for the given value of x. So this is the notation we're going to see. It does not always have to use the letter F. You can see any letter of the alphabet, G, H, whatever. And then the input value is typically X, but again, that could be another letter. Okay, it could be any letter of the alphabet. So our first example, we're given a function that they're naming g. So the definition we're given is g of x is equal to x squared minus 10x minus 3. And we're asked to evaluate it using function notation for different expressions. So our part A says find g of -1. So it's telling me the x value is -1, and I'm looking for what I would get if I were to plug -1 into my function in place of g. I'm sorry, -1 in place of x into g. So g of -1 means replace all the x's with -1. So -1 gets squared, subtract 10 times -1 minus 3. Right, here's my x places that I'm plugging in my value. And then we simplify. Square -1 is +1, minus, or -10 times -1 is plus 10, minus 3. So 10 plus 1 is 11, subtract 3 would be 8. In our next two examples, we're substituting in an expression. Does not change the meaning of what function notation says. This says evaluate the function g by replacing the x with the expression x plus 2. So g of x plus 2 means up here in our given function that we were given for g, we replace x with the expression x plus 2. So So we get this time x plus 2 squared minus 10 times x plus 2, again for x, and then minus the 3. And then you're going to simplify. So x plus 2 squared, remember, means x plus 2 times x plus 2, so we're going to have to FOIL. X times x is x squared. The x times the 2 is a 2x on the outer, and then the inner is another 2x. So that outer 2x plus the inner 2x is the 4x. And then on the very end, we just get 2 times 2, which is 4. Here we're just distributing the negative 10, so minus 10x. Be careful here, this would be minus 20, and then minus the 3. And then from here we're collecting like terms, so we have an x squared, we have a 4x minus a 10x, which is negative 6x, and then 4 minus 20 minus 3 is negative 19. That's as far as you can go. You are just evaluating g of this expression, so your answer should contain x's. You don't set this equal to anything. There's no other steps. This is just the result from doing what the problem asked us to do. In our third one over here, we have g of negative x. So this time we're replacing all x's with negative x. So negative x squared minus 10 times negative x minus 3. So when I square negative x, I get positive x squared. Squaring the negative 1 is a positive 1. Squaring the x is x squared. Negative 10 times negative x is plus 10x minus 3. And there are no like terms to collect, so we're done. That's it. So our next example is the same type of problem. So we have f of r, so they're just using r as the input this time instead of x, is equal to the square root of 25 minus r minus 6. So let's start here with part A, f of 16. This means replace r with 16. So the square root of 25 minus 16, and then outside the square root is the minus 6. Clean up underneath, gives me 9. Square root of 9 minus 6, that square root value is 3 minus 6, negative 3. Part B is similar. This time we replace r with negative 24. So the square root of 25 minus, plug in negative 24 for r, so be careful. This minus is part of the given function. We're plugging in a negative number for r, minus the 6 outside. So the two negatives turn to a plus sign. Adding those together gives me a 49 under the square root. Square rooting 49 is 7, and then the minus 6, 1. And then again, part C, we're plugging in an expression. So 25 minus 2x is replacing r. So the square root of 25 minus, we substitute 25 minus 2x in place of r. And you have to be very careful here since you're substituting in this entire expression, and before the r is a minus sign, you must put that expression in parentheses or else your simplification is going to be incorrect. And then follow it with the minus 6. So when we're cleaning up under here, the negative has to apply to all of this. So we're going to distribute this negative sign. So we have the 25 minus 25, and then the negative times the negative turns this to plus 2x. That's removing the parentheses. Then the 25 minus 25, those cancel, so they go away. So you're just left with 2x under the square root sign. So we have the square root of 2x, and then behind it is still the minus 6. And there's nothing more we can do in terms of simplifying. All right, so I'm going to stop the video here for part 1, and then I will do a separate video to cover part 2 of section 2.1.